Hey, last time we introduced the notion of a force, and what I showed you was how to go from again we have this transition from the world of Newton and Euler, and here it was in the context of forces and torques. To produce a single object, which we call the Lagrange force. Okay, so it's a way of conglomerating into one thing all of the separate forces and torques for your system. Okay, so today what we'll do is we will see how to actually calculate the Lagrange force in some simple examples. Okay. And so we're going to work first with our simple planar rigid body example, like so, with center of mass at the origin of the body frame as usual. Okay, and I will consider on the body a force, and the force is going to be applied at a point here, and I'm going to choose this point for convenience by making its distance, some distance, let's say h, away from the center of mass along the body B1 axis. I don't have to do that. I could put it wherever I want, but by orienting the body frame appropriately, I can ensure that it looks like that. Okay. And so I'm going to apply a force there, and the force is going to be, so it's applied at that point. It's going to have some amplitude F. And I'm also, and sorry, there's also, in terms of the data I need to describe this thing, there's going to be some angle here, which I'll call phi, which is the angle of application of the force to the body B1 axis. Okay. So I have a force that's applied like that. And again, as I talked about last time, that force can depend on lots of things, but for the purposes of our discussion here, we'll just assume that it's a function of time. Okay. And then we could also think about applying just a moment to the body. Let's call that tau. Okay. All right. So there are two forces here. Okay, let's sort of agree to call both forces and moments forces in some general way. Okay, so there's the force F and the torque tau. Okay, so for the force F, we have F1. Okay, so maybe let me make it clear what I'm talking about here. For the force F, okay, I have F1. So a force can, as we saw last time, it could possibly exert a force and a moment. And the force, which we call little f, is always applied at the center of mass. Okay. And so what I have to do is I have to write the vector F1, okay, which is just going to be the direction of application of this force, and the length of the vector F1 will be this thing, capital F. All right. So what this means is that F is equal to F, so that's the amplitude of the force, and then the direction that it points is, well, we previously had a theta here, right? And so in the spatial coordinates, the angle of the force F is theta plus phi. Okay, so I'm not measuring that in body coordinates, but I'm measuring it in spatial coordinates. Right? So it's cos theta plus phi sine theta plus phi 0. okay? And then it also has a moment, okay? And that moment is going to be, so, you could, first of all, get the formula that I wrote last time in terms of when you translate a force to the from one point to another, in this case, the center of mass, there's a moment which is, and I said it was either tau cross r or r cross tau, or you can just sort of go back to elementary first year physics here. And the moment exerted by this force about the center of mass is you're going to take this component of the force, okay? And why is it this component of the force? It's because that's the vector orthogonal to the vector which connects this point to the center of mass, okay? So you're going to take this component of the force and multiply it by that distance, okay? So just standard first year physics, okay? So what that will be is that amounts to f sine phi, and we have to write this as a vector in R3. And so what that means is I have to write it as two things. One is an amplitude and one is a direction. And the amplitude is going to be the thing that I was about to write down, which is f sine phi times h. And then what's the vector going to be? Okay, so the vector is going to be the axis about which this rotation is occurring. And what axis is this occurring about? Just the spatial x3 axis, right? So 0, 0, 1. Okay. All right, so that's the force and torque corresponding to the force F. Okay. All right, then I have the torque tau. And again, it'll have a force associated to it, and it'll have a torque associated to it. But the force of a torque is 0, always. Okay, and then the torque of a torque is the torque. So it's about the axis S3 again, so it's just tau times 0, 0, 1. Okay, so that's the first thing you do is you take the physical data and you convert it into Newton-Euler force torques, like we talked about, vectors in R3. Okay, and then once you have those, then you can write down the power. Okay, and remember, to write down the power, you need these things. Okay, and you also need the spatial angular velocity. Okay, and you need the translational velocity. So we calculated those already for this example, and of course they're very simple anyway. Okay, so we had calculated that r dot was x dot, y dot, 0, and that little omega was 0, 0, theta dot. Okay. All right, so then the power, okay, is that you just take the forces, okay, so you sum over the various forces. And so here it's going to be when we wrote this formula down last time, we wrote it as a sum over bodies. Here we have a single body, but on that single body are two forces. Okay, so we're going to do a sum over the forces. All right, so it's going to be the sum, j equals 1 to 2. Okay, so it's going to be F1 r dot. Fj r dot plus tau j omega, like so. Okay. All right, so there's a single body, but on that body are two forces. All right. So now this is just an elementary calculation, right? So I'm just taking the inner products, right? So this bit is going to give me F1 and F2. Okay, F1 is is that expression. F2 is 0. So this thing is just going to be the inner product of F1 with R dot. Okay, and that is, so it's going to be F, sorry, it's going to be just a scalar. So it's going to be F X dot cos theta plus phi plus Y dot sine theta plus phi. Okay, so that's going to be this term. All right, then I'm going to get the taus. Right, so I'm going to get a contribution from that one, and I'm also going to get a contribution from this one. All right, so that's going to be plus. Oh, sorry, I got a. I apologize. I made a sign error here. Right, the way I've drawn F as positive, pointing in that direction. So its component in the direction orthogonal to the vector to the center of mass, which is that, that'll actually exert a counterclockwise torque, right? So that actually should have been a minus sign there. Okay, does that make sense? Or just using the right hand rule. Okay. And so what I'm going to get here is I'm going to get a minus F sine phi plus tau times theta dot. Okay, so that's just taking inner products. Okay, so what I'm going to do now is I'm going to organize that so that x dot, y dot, and theta dot come out as coefficients. Okay. And so this is equal to, so x dot is going to have a coefficient, and that coefficient of x dot, and you'll see why we want to organize it this way in a second. Times x dot. And then for y dot, I'm going to get f sine theta plus phi y dot. And then finally, I'm going to get just tau minus f sine phi theta dot. Okay. All right. So that's nothing. I just reorganized it slightly. Okay. Now, so that's the power. That's fine. But now what we do is we use that expression to calculate the Lagrange force. Okay. All right. So to calculate the Lagrange force, F, okay, well, we write down F as being one of the things that it is. And what we decided last time was that the Lagrange force was a covector field, you know, along the curve, but let's just forget about the little detail of that, and let's just write F as a covector field, okay? So we're gonna write F as Fx dx plus Fy dy plus F theta d theta. Okay, and the thing is we determine what Fx, Fy, and F theta are. Okay, and you do that by simply requiring that the definition of the Lagrange force hold. Okay, which is we ask that F a gamma prime is what we had in our definition. Okay, but we're doing everything here in coordinates x, y, and theta, and in coordinates gamma prime will be as a tangent vector field. It's going to be x dot d by dx plus y dot d by dy plus theta dot d by d theta. Okay, and so remember the semicolon notation means covector field here, vector field here. Okay, so it's this covector field, which I've written out here, which takes as an argument that vector field. Okay, and that should equal the power. Right, so this is going to be equal to f cos theta plus phi x dot plus f sine theta plus phi y dot plus tau minus f sine phi theta dot. Okay. So now you can just calculate this directly from here, right? So if I take fx d by dx plus fy d by d theta plus f theta d by, sorry, if I take fx dx plus fy dy plus f theta d theta, and I act on the tangent vector, x dot d by dx, y dot d by dy, theta dot d by d theta, what am I going to get? Well, I'm going to get, by using the fact that, first of all, f is linear, okay, so I can distribute all of these sums here, I can expand them all out, okay, and so I'm going to get fx d by dx acting on that whole thing. But I know that dx kills d by dy, and it kills d by d theta, and it takes that and gives me 1, okay, so I'm going to get fx x dot. All right, and then similarly, dy takes this, it kills d by dx, it kills d by d theta, and takes d by dy and gives me 1. So I'm going to get fy y dot, and of course f theta theta dot. Okay. All right, so that's just, using the definitions of all the symbols involved. Okay, and so now you can see why I organized it sort of carefully in this way, and that is because now you can just read off the coefficients of x dot, y dot, theta dot to get fx, fy, and f theta. Okay. All right, and so finally, therefore, just putting it all together. Okay, and so this is the Lagrange force. All right, so the calculation here is extremely simple. The only thing you have to do here that requires thought is the very first step, where I convert my physical data of what those forces and torques are into Lagrangian and into Newtonian and Eulerian F's and taus. Okay, the rest of it is just rote calculation, and so again, it lends itself to a computer doing the calculations for you. Okay, good. Let's look at a different example. All right, so of course we're going to look at our stupid robot example. Okay. All right, so there's a natural set of inputs or forces that will make this thing move around, and that is that you put a motor here and you put a motor here. Okay, and so what are those going to do? They're going to give you a torque, and so because I want to use taus for torques, let me denote this torque by T1. so that I don't get confused with taus, and this one by T2. Right? So that means I have a motor attached to the ground and also attached to this point in this arm of the robot. Okay, and it applies a torque to the arm, and then I have a motor between these two bodies attached to each, which actuates the relative angle of that joint. Okay, so let's convert that physical data into Newtonian and Eulerian F's and taus. Okay, so torque T1. Okay, and so we're going to sort of think that everything has potentially two bits to it, a force and a torque. So there's going to be an F1 and a tau 1, but F's for torques are 0, of course, so that makes our life easy. Okay, and taus, okay, so this is going to be a torque in the way I've drawn it, counterclockwise like this. It's going to be T1, 0, 0, 1. Okay, so it's going to be a torque applied to the first body. Okay, oh, and I'm sorry, I need to be a little bit more careful here than I was in the example above, because in the example above I only had one body, and so I didn't have to think about whether these forces were applied to body 1 or, excuse me, to body 2. And in fact, I need to bookkeep that here. So this is going to be F1, okay, meaning it's the first force corresponding to T1. Then it's going to be how it acts on body 1, okay, and then the torque similarly corresponding to that is going to be the torque for T1, which is that index acting on body 1, right? Then there's also going to be 1, 2, and 1, 2. Okay, so this is how this torque applied here acts on body 2. Okay, now you can make this super complicated, and you can try to think about, if I apply a torque to body 1, then it transmits through the link and applies a torque to body 2. But the whole point of this analysis is you don't do that. Okay, the only place where that torque is applied is it's applied to body 1. Okay, that motor is not connected at all to body 2, only through body 1, but that gets taken care of by the magic of Euler-Lagrange equations. The torque acts only on body 1, so these are both 0. Okay. All right, so it's careful not to overthink these things. Okay, but it's also careful not to underthink them, as we'll see here. Okay, because this torque, okay, this motor is physically attached to body 1, and it's also physically attached to body 2. Okay, so it's actually going to have some stuff in both bits. So there's going to be an F2. Okay, so this is the label for the second torque, and then there's body 1. There's going to be a tau 2, 1. There's going to be an F2, 2, and a tau 2, 2. All right. So there's, in general, lots of stuff to keep track of here, but as we know, for torques, the forces are all going to be 0 anyway, automatically. All right. So the only thing we have to think about are how the torques work. Okay. All right, so this torque, which I've drawn as T2, like I said, it is applied to both body 1 and body 2. Okay, so I have to make a choice here about whether that torque acts in the positive orientation on body 1, or it acts in the negative orientation on body 1. So in other words, if T2 is positive pointing in that direction, how should I interpret that as what's happening to body 1? And then there's a choice there, and I'm going to go T2, 0, 0, 1. Okay, and the only thing that matters here is that same torque, T2, when applied to body 2, if it was positive applied to body 1, then it's going to be negative applied to body 2. Okay, and the idea is that you're using Newton's laws about equal and opposite reactions. Okay, all right, and so this one's going to be minus T2, 0, 0, 1. Okay. All right, so it doesn't really matter. I mean, it matters when you implement it, and that sort of depends on whether you're thinking of yourself as being attached to body 1 when you apply the torque from the motor, or whether you think of yourself as being attached to body 2. That'll determine which of those two choices you make. Okay. All right. Okay, so in this case, you see we have a lot of data, but most of it is 0. Okay, good. So then we write the power. Okay, so the power has lots of bits to it. And so here what I'm going to do, and I could have done that up here too, but I didn't do it kind of on purpose because I wanted to show that I have these two forces, and I want to take the power for both of them. Okay, but what you notice here is, and you really only see it in this part here, because that's where the two things are combined. That's the only place where this force and this force are combined, is in that expression right here. And I could actually have just taken F1 and F2 and added them, and I could have taken tau 1 and tau 2 and added them to get a total force and a total torque. So let me do that. Okay. Let me in. Okay, so what this means is on body 1, we have the force F1, okay, and F1 is going to be F1 plus F2 1. Okay, because that's the way I've numbered things. Okay, so when I numbered these guys, this was the body, and this was the which of the two forces I was talking about. Okay, so F1 is that. So I can just directly add these. Okay, and when I do that, I just get, because F2, 1, well, sorry, in this case, they're both forces. They're all 0 because it's just torques. Okay, and then we have tau 1. Okay, and tau 1 is going to be tau 1, 1 plus tau 2, 1. Okay, now this one gives me something interesting. So it gives me T1, 0, 0, 1. Okay, plus T2, 0, 0, 1. Okay, so in other words, it gives me 0, 0, T1 plus T2. Okay, does that make sense? All right, and similarly for body 2. Okay, I have F2 is F1, 2 plus F2, 2, and the forces here are all 0. And I have tau 2 is tau 1, 2 plus tau 2, 2. Okay, and tau 1, 2 is 0, right? And that's because the torque T1 doesn't actually act on the second body. And then tau 2, 2 is this thing. So it's 0, 0 minus T2. Okay, all right, so that's just adding forces and torques. And you can just add these as vectors, is the point. Okay, then you can write down the power. And now you write down the power as a sum over all the bodies. And you know, you could write this as a double sum, right? So here I wrote this as a I wrote this as a sum, right? But it was a sum over the number of forces that I had applied, but there was only one body. But here I could have also written this as a sum over the collections of forces. Okay, and then also summed over the two bodies, but I've sort of taken the double sum and I've cleverly broken it up into two single sums. All right. Okay, so then the power is, okay, so it's going to be sum now over the bodies, A equals 1 to 2. Okay. And so it's going to be FA, and so these are the F's that I just calculated here, F1 and F2, times RA dot. All right, so these are the RAs that are the little r's, you know, differentiated with respect to t, the velocities of the center of mass that we had previously calculated. So there's kind of ugly expressions for these, but thankfully the F's are 0, so they don't matter. Okay, and so the only thing we're going to get are these ones. Okay, and of course we had previously calculated that the omega a's are 0, 0, theta a dot like this. Okay, and so now it's just a question of doing inner products. And like I say, this one's going to be 0, and you know, this is just vectors with only things in the third component, right? So the point is, it's all going to be quite simple. You're going to get T1 plus T2 times theta 1 dot. Okay, so that's going to be tau 1 inner product with omega 1. Okay, and then for tau 2, I'm going to get, minus T2 theta 2 dot. Okay. All right, so therefore, so, you know, I did this elaborately in the first example, right? So I wrote out the Lagrange force and, you know, calculated all of this stuff, and then, you know, calculated the coefficients. But the point is, as soon as you have the power written down with the coefficients of x dot, y dot, and theta dot, those are going to be the components of the Lagrange force. So I can kind of skip all of this because it's unnecessary, but I wanted you to show why. I wanted to show you why it was unnecessary. Okay, and so the Lagrange force is T1 plus T2 d theta 1 plus, minus T2 d theta 2. Okay. All right, so that's how you calculate the Lagrange force, right? So then the question becomes, how does Lagrange force enter the equations of motion? Okay. All right. All right, now we talked, when I wrote down the Newton-Euler equations, you know, the conservation of momentum equations for rigid bodies, I had added forces and torques on there, and I was a little bit not clear about what I was talking about, and that's because we hadn't really talked about force and torque at that point, but now we have. So we can be a little bit more careful about talking about that now. So first, let's see how we add forces to the Newton-Euler equations. Okay. So for a single rigid body, okay, we had that the equations of motion were, you know, basically F equals ma, but the appropriate version of that. Okay, ma was the time derivative of the momentum, and there's two components of the momentum. There's the translational momentum and the angular momentum, and F is F. And the F's there are the little f's and the little taus that we've been talking about, right? So it's little f is sort of the conglomeration of all the possible forces, right? So, like in this example here, I had two kinds of forces that I was applying to my system, and then I conglomerate them all into one thing, which would be in this case F1 plus F2 and tau1 plus tau2. All right, so that's what little f is in that formula. It's all the forces acting on that rigid body added together, applied at the center of mass. Okay, and then in the angular momentum equation, you're going to have all the taus added together. Okay, so okay, so for a single rigid body, we're going to have d by dt of mu, and remember that mu is the spatial angular velocity. And there's a formula for that, and I'm probably going to get, well, I have a 50-50 shot at getting my transposes in the right place. Mu is r, so let me put the time arguments in here. R of t, it's r of t, inertia tensor about the center of mass, r of t transpose times the spatial angular velocity. Okay, and so I don't know if the transpose goes here or here. Okay, so that was the expression for the spatial angular momentum. All right, so and then so I'm going to write it as mu, not as that big ugly thing. And the point is that's equal to tau. All right, and then similarly, I have the conservation of translational momentum, but not conserved anymore because forces are applied. And so that was P of t is equal to F of t. Okay, and this P of t is the translational momentum. And this one is just, you can take it to be P of t is m r dot of t. Okay. All right. And the most important part of this is these are the same f's and taus that we talked about when we calculate the Lagrange force. Okay. All right. Now, suppose we have an interconnected system. Okay. All right, so I have m bodies, and so the equations of motion are going to be these, except I'm going to have m of them, one for each body. And also, I'm going to be a little bit more careful about my forces and torques here, because I'm going to take my forces and torques, I'm going to break them down into two parts. Okay, there's going to be the externally applied forces and torques, which in our first version of the equations of motion were assumed to be zero. And then there's going to be the interconnection forces and torques. Okay, so I talked about this a little bit before, but now since I've actually told you what forces and torques are, we can talk about it a little bit more carefully. All right. And so the equations read the same as the equations I had above, but just with increased resolution and with an index. All right, so it's d by dt mu a. Okay, so the spatial angular momentum for body A is going to be, right? So there's going to be an external force, which I'll call FA. Sorry, this is the torque equation. An external torque, which I'll call tau A. And then there's going to be an interconnection torque. And I'm going to write these as iota. Okay. And so this has to, first of all, there has to be one of these equations for each body. Okay. And these are the external torques. And these are the interconnection torques. Okay, the torques which we dedicate to holding the system in the configuration prescribed by Q. Right? And I'll say some more words about exactly what makes something an interconnection force or torque. Okay, so that's the angular momentum equation. Then, of course, there's the translational momentum equation. And again, I'm going to have one for each body. Okay, and this is the external force. And this is the interconnection force. All right. All right, so like I said, in order for this to really make sense, I need to tell you, how do you distinguish between an external force and an interconnection force? Well, external forces, first of all, are something you typically know, right? So they're user prescribed, all right? So I have a motor and I'm applying a torque at a joint like I was in the robot, or I have a force like in the first example applied to a point on the rigid body. Okay, so you don't often have much difficulty knowing what the external forces and torques are. They're prescribed by either by nature or by the user. Okay, and the interconnection forces and torques, they are things that you solve for. Okay, and they can't just be arbitrary. All right, they have to have a certain property that makes them an interconnection force or torque. Okay. So what makes an interconnection force or torque? Okay. And there's a sort of physical principle which goes under a few different names, one of which is the principle of virtual work. And I'll sort of write it down in sort of words and then tell you what it means. Okay, so the principle of virtual work says, if you Google principle of virtual work, it definitely won't read like this. But what it means is that interconnection forces and torques do no work on admissible motions. So that's the English language version of it. And I'll now convert that into mathematics. Okay. All right, so what this means is this. Okay, so let gamma be, gamma is of course a curve. be any motion of the system. Okay, not necessarily a motion that satisfies, the equations of motion, right? Just any motion of the system. Okay, so then I have of course, as we've talked about on on multiple occasions, we have the little r's and the big R's are determined from the curve gamma by the forward kinematic maps capital pi. All right, and so therefore we can calculate RA dot of t and little RA dot of t. And again, this is something we've done on at least 2 occasions now. One when calculating kinetic energy, which I did fairly explicitly in that case. And then in the last lecture, we also talked about this. I didn't sort of write it all out because I'd written it out before, sort of saying that you calculate these, of course, by differentiating that equation with respect to t. And upon that differentiation, the formula you get is this. You use the chain rule. So you get the derivative of pi a, and the derivative is, remember, t for us. And then you differentiate gamma. The derivative of gamma with respect to t is gamma prime. Okay. All right. So the point is this, is that if you have a motion which satisfies the interconnection constraints, and all that means is that it is a curve in Q, okay, then it'll have a velocity, right, which means that you're going to have some RA dots, capital RA dots and little RA dots, and then you're also going to be able to back out omega A and RA dot. Okay, so omega A, you of course is the spatial angular momentum, and you calculate that from capital RA and RA dot. Okay. All right, so the point is when you have a motion gamma that satisfies the interconnection constraints, and again, all that means is that it's a curve in Q. Okay, then you're going to have a corresponding omega A and RA dot. Okay, and so interconnection forces and torques then are required to satisfy exactly the principle of virtual work, which says that these forces and torques do no work on admissible motions. And so, but instead of writing that as work, we of course use power, but the idea is the same. Okay, so it's just the sum, A equals 1 to M. Sorry, the interconnection forces and torques are rhos, so rho A of T, R A dot of T plus iota A of T, omega A of T is 0. Okay, so really what this is, and this has to hold for all possible RA dots and all possible omega A's that come from any admissible motion. And this is kind of an orthogonality condition, right? It's saying that these forces and torques, okay, need to be orthogonal to the velocities that come from admissible motions. And this is the condition of doing no work. Okay. So notice then that the corresponding interconnection Lagrange force. Okay, so I take all these rhos and iotas and I convert them into a Lagrange force in exactly the way that we have been doing. And I'm going to call that capital I, okay, sort of keeping with interconnection language, satisfies that I, remember, so I is a cotangent vector field. When you apply it to gamma prime, that's equal to 0. Okay, so these two equations are saying exactly the same thing. This is the Newton-Euler version of the principle of virtual work. Okay, and this is the Lagrangian version of the principle of virtual work. Okay, all right, so we will continue chatting about this next time.